Swayam Prabha. Digital India. Educated India.
Hello everyone. So we'll continue with our numerical part of constant tension winding test. Here in this numerical, the example is that the tenacity is given. So tenacity of 30 tex cotton yarn is 5 inch. At 5 inch gauge length is 25 centinewton per tex. So at 5 inch gauge length, the tenacity is 25 centinewton per tex. In the constant tension winding test, the breakage rate is given 25 breaks per 1000 yard at tension 40 centinewton. Okay. At 20 inch gauge length, what is the tension required? The breakage rate will be 15 breaks per 1000 yard. So at 20 inch gauge length, we want to get the tension required to achieve 15 breaks per 1000 yard. So assume the standard deviation of the single yarn strength is always 30 centinewton. So for any gauge length, the standard deviation will be 30 centinewton. Now let us try to solve this numerical step by step. First, the derivation is given here. So from this derivation, the T is the tension required to achieve X breaks per 1000 yard, that we know, and T1, T2 are the tension on which the tests were performed. So N1, N2 are the breakage rate at constant tension T1 and T2. From the given condition, T1 is given here 40 centinewton and the breakage rate is 25 breaks per 1000 yard. So this will become T1 and N1. And to satisfy this equation, as I have already mentioned, T equal to X bar minus 3.3 sigma standard deviation. So if we want to convert the static strength to dynamic strength, we must use this relationship, but to satisfy this, we need two conditions. We need the gauge length as 20 inch gauge length and breakage rate 8 breaks per 1000 years. Now try to reach to this condition. So N2 is 8 breaks per 1000 yard at gauge length 20 inch. That is considered as N2. Okay. And X bar is that this X bar is the mean single yarn strength. Standard deviation is given 30 and yarn linear density is 30 tex. So yarn tenacity is 25 centinewton per tex. So the yarn breaking load X bar will be 750. 750 is the breaking load, static breaking load. But what it is given, it's at 5-inch gauge length. So in the given numerical, this 25 centinewton per tex is at the 5-inch gauge length. But our condition is that we should have 20-inch gauge length. 20-inch should be the gauge length. So at 5-inch gauge length, if the strength is 750 centinewton, then to convert it to 20-inch, so we must use the relationship. Given relationship was, this was the relationship that we have discussed, where R will be 20 by 5. 5 is given, we want to 20, so R times, R is 4. So here we use R value, and this load SL is at 5-inch. This is at 5-inch, and RL is the strength at 20-inch gauge length. This is at 5-inch gauge length. That we have already discussed in detail. So from there, we can calculate the XRL. If we know the CV percent, because we know the standard deviation was given. Okay, the standard deviation was given 30. 30 was the standard deviation. So coefficient of variation V we can calculate, and the strength at 20-inch gauge length is 692.79. From the above equation, the tension required to achieve 8 breaks per 1000 yard will be 692.79. That is the static strength, 3.3 is a factor, and standard deviation. So this is the tension, 593.69 is the T2, and N2 is 8 breaks per 1000 yard, because the condition is that the 8 breaks per 1000 yard to be used, and gauge length 20 inches to be used, then only we can get the value. So the number of breakage, 8 breaks per 1000 yard, so it will be, say, N2, and T2 is given. So earlier condition T1, N1 was given, so we can use the given relationship here. So T1 was 400 centinewton, and N1 was 25 breaks per 1000 yard, which was given. T2 we have calculated 593.79 centinewton for 8 breaks per 1000 yard, because we have used the constant K as 3.3. As we have used constant K 3.3, so it will automatically represent the breakage 8 breaks per 1000 yard. And for winding tension T, the breakage rate will be 15 breaks per 1000 yard. So what will be the winding tension? So this will be 400 T1, T2, T1. This is the breakage rate X, and this is N1, N2. Sorry, this is N1. So log X, and this is N2. This will be N2. We have seen this is N2, and by solving this equation, we get the tension required to have 15 breaks per 1000 yard, 486.91 centimeter. So this type of numerical, we can identify that when the static strength is given, in this relationship here, no static strength is considered. Here only dynamic tension is considered, tension required to have certain breakage. See, in this equation, so only tension and the breakage rate is discussed, but when the static strength is given, so we have to convert this static strength to the dynamic tension using this formula, this relationship, and in this relationship only if we want to use 3.3, there we have to get into the conditions, that is 20-inch gauge length and 8 breaks per 1000 feet. So accordingly, we have calculated the required tension. Okay. Now our next numerical is similar. We have already done this type of numerical. So during cone winding, the breakage per kilometer of yarn was observed to be 40 and 80 at the winding tension of 400 centinewton and 500 centinewton respectively. So to bring down the breakage rate to an acceptable limit of 20 breaks per kilometer, what will be the winding tension? It's very simple. We can directly use the relationship. Winding tension breaks per, so this N1 is 40, N2 is 60. Okay. So breakage breaks per kilometer, break per kilometer, and tension T1, so N1 N2, T1 equal to 400 centinewton, T2 T1, T2 is 500 centimeter. Okay. And X is equal to 20 and T we need to know. So this is the relationship. X is this. So this is given. Okay. And we use the relationship here and to get the tension. So the tension becomes 220 centimeter. So 229 centimeter. Okay. To have 20 brakes per kilometer. Next numerical is that again the similar numerical. Here tenacity is given 20 takes yarn. For 20 takes yarn is 15 cm per takes with a gauge length of 4 inch. So at which tension in the constant tension winding test the breakage rate will be 20 breaks per 1000 yarn. Okay. So what, assume the standard deviation of single yarn always 20 cm and at 200 cm tension the breakage rate is 0.5 breaks per 100 yards. So for 1000 yards, so 0.5 breaks per, so T1 will be 200 cm, so N1 will be 0.5 breaks per 100 yards, that means 5 breaks per 1000 yards. So the similar numerical we have already done. So T can be calculated using T1 200 cm, N1 5 breaks per 1000 yards. We have to reach this target value and to use K as 3.3. What is the target value? 20 inch gauge length and 8 breaks per 1000 yards. So we will get the breakage rate 8 breaks per 1000 yards at gauge length 20 inch. So here our gauge length is 4 inch. So we have to calculate the strength at 20 inch gauge length. So strength at breaking load at 4 inch gauge length is 15 multiplied by 20 takes, so 300 centimeters. Okay. What will be the strength at 20 inch gauge length? That let us see. 20 inch gauge length, standard deviation is given. So 4 inch gauge length is 300 centimeter. So the ratio R will be 5 times the gauge length here. So in this equation, if we subtract here, so if we substitute R value as 5, so we will get the SRL, that means the strength at the 20 inch gauge length will be 265.3. It will reduce, so 5 inch gauge length it was, so 4 inch gauge length it was 300, at 20 inch gauge length it will be 265.32, and using the K value as 3.3, we will be able to calculate the tension required. Tension required T2, so is 199.32. This tension is required T2 with the breakage rate will be 8 break per 1000 yards as per the condition. Only in this condition we will get the K value 3.3. So N2 is known. So from this equation, so we will be able to calculate the tension required. So tension required will be 197.99 centimeter. Okay. So to have 20 breaks per 1000 yards, so 20 breaks per 1000 yard, it will be 197.99. Now, another numerical here, following are the results of tenacity centinewton per text of 10 specimen of 20 text cotton yarn with 10-inch gauge length. So these are the tenacity values, 16.71, 15.9. These all are the tenacity values. Now, the approximate tension required centinewton during the constant tension winding test to have 8 breaks per 1000 yard is 20 inch with 20-inch free length, that is gauge length, is that we want to calculate. So 10-inch gauge length, this is the result. So first let us calculate the mean value. The mean value will be 325.1. Okay, and standard deviation here is 5.63. So this is the C. And here we can calculate the CU percent. The CU percent here is 1.73%. So breaking load at 10-inch gauge length is 325.1. So let us calculate the breaking load at 20-inch gauge length. That means R will be 20 by 10, the length ratio. So R is 2, and using this relationship we can calculate the breaking load at 20-inch gauge length, which is 322.04. At 10-inch it was 325. Okay. So using this relationship, okay, to use the K value as 3.3, so the tension required to achieve 8 breaks per 1000 yard becomes 303.46, because when you use 3.3 and we use say 20-inch as a gauge length, automatically the breakage rate will achieve 8 breaks per 1000 yard. So this is all about the dynamic test. Now we will discuss the yarn strength. So single yarn strength is measured in universal tensile machine. So 500 millimeter gauge length in universal testing machine, and speed is adjusted so that the time to break is 20 plus minus 3 seconds, and gauge length is 500 millimeter. And in Lee method we can use, or Skein method, where we form the Lee of yarn and then we break. The advantage here is that in Lee tester it tests long length of yarn in one test. In single yarn test when we test say 500 millimeter or 50 centimeter, in Lee test in one go you can test 120 yarn at a time. We can get the information of the yarn strength of 120 yards, and where we will be able to assess the performance at different weak spots. But 120 yards there will be number of weak spots, so that the overall assessment we can have. And this same hank which we have, same Lee, this is a Lee we normally test, same Lee we can use for count measure, so that we don't have to use other yarn. So in the Lee strength method, so CSP is measured. What is CSP? CSP is breaking load of Lee in pound and yarn count in N. That's the definition of CSP. Now CSP, looking at the fact, it's very simple. It's a product. So it's not an arbitrary value. Although it looks very simple, but it has got some logical meaning. Why not it's a division, say breaking strength by count? It's not the fact. Here the logic is that for a particular variety of cotton, the CSP for a certain range of yarn count is almost constant. CSP value is constant within a certain range. Okay, that means suppose a yarn of say 40 any yarn is giving CSP of say 50, so Lee strength of 50 pound. 50 pound Lee strength, 40 any yarn. So CSP will become 50 into 40, so around 2000. 2000 is the value which represents the variety of cotton to spin say 40 any count. So for a particular variety of cotton, if we spin 40 count, it will result CSP 2000. Now, tomorrow some other lot, if we don't get CSP 2000, around 2000, say plus minus 100, within that range, that means we can guess, okay, that the cotton quality is poor. Similarly, CSP also tells us about the count spinability. For a particular variety of cotton, a count range say 30 to 40, 30 any to 40 any, for a particular variety of cotton we can produce. And if we produce say 30 count, 30 any from the same cotton, the strength will be increased proportionally. As the yarn becomes coarser, so CSP value will increase proportional load, breaking load value will increase proportionally, maybe around say 68 or 70. So if it is 68, so 30 multiplied by 68 will be around 2000. 30 multiplied by 68 is 2040. Okay, that means we can guess from this yarn we can produce 30 count also, and also from this fiber we can produce 40 count. Now if we try to produce same 50 count from this fiber, and we are expecting the strength to be 40 pound, so that we can get the CSP around 2000. But if this fiber is not within that range, if we are trying to overspin, so this will not get 40 pound, we may get much lower, say 20 pound, which will result CSP of say 1000. So for a particular cotton, we are expecting the CSP of 2000, but we are getting a CSP 1000. That means we are overspinning the fiber. So this fiber is not suitable for that 50 count, that much finer count. So CSP is an indication. So this is an indicator which will give us the idea about the variety of cotton, machine performance, and also the count range. So for a particular cotton fiber, one machine is producing say 2000 CSP, and other machine is producing say 1500 CSP. That means the performance of that machine is not optimum. So CSP tells us many parameters. Okay, so for a certain variety of cotton, CSP value should be almost same. It also shows the optimum count possible. So count range I have discussed from a particular variety of cotton. So CSP value indicates the overall performance of the spinning. So CSP, apparently it looks very simple, but it has applicability in the practical applicability in the industry. The main disadvantage is that it depends on the friction between yarn. So yarn with higher friction will give higher strength value and higher CSP value. That is one disadvantage. And within strand variability we will not get, we will get one average value. Now the example is that the least strength of a 40 tex yarn is 40 kg. What is the CSP? So 40 tex yarn, and we want to calculate the CSP. The CSP by definition is a load in pound, breaking load in pound, and yarn count in NE. So 40 kg we have to convert it to pound value, and 40 tex we have to convert into tex value. Then we multiply. So 40 tex is equal to 14.76 English count NE, and 40 kg breaking load of Lee is 88.18 pound. And from there, by definition, if we multiply, we get the CSP 130153. So we must remember the CSP is only the multiplication of the product of strength in pound, least strength in pound, and the yarn count in any, and this is calculated based on only Lee of 120 yards. If we change the length of the yarn, that is, if we take 100 yard or 50 yard or 200 yard, then we will not call it a CSP. Although there will be count and strength product, but by definition, so you can use count set single yarn count 20 any and strength maybe 0.5 pound. If we multiply, this will not be a CSP. Although we are multiplying count and strength in pound, but still it will not be CSP. The strength of Lee should be there, Lee of 120 yard. Again, the similar numerical where the linear density is given in metric count and strength is given in kg. So metric count, we convert it to English count, 23.6 NE, and 40 kg is 88.18 pound. So CSP is 2081.04. Now another tensile testing, that is for fabric tensile testing. So in fabric tensile testing, we have observed that during tensile loading, initially the fabric is rectangular in shape, but while applying load during the extension, there is a deformation at the center. So this effect is known as wasting effect. Okay. Wasting effect, and this is due to the crimp interchange. Suppose longitudinal yarns are say warp. When we stress, when we apply load towards the warp direction, the crimp in the warp yarn reduces due to the load, but that crimp is transferred to the weft yarns, which gets contracted. Let us see the animation here. And the fabric is being placed here, and the load is being applied. We have clamped it. Now loading is done. So due to crimp interchange, the wasting effect, and then breakage stretches. Okay. And this, as we have discussed, see, after reaching peak load, still it is carrying some load, but we will consider the peak load as the breaking load. So typical sample size is 60 millimeter by 300 millimeter, and after fraying out the edge fibers, the width is bring down to 50 millimeter. This is done because to ensure that no cut threads are there at the edge, both the edges. So 50 millimeter width means we are taking out the threads from the edge 5 millimeter from each side to ensure that the both the all the threads are being gripped by the jaws. So sample is pretension. These are the methods. Now let us try to solve numerical related to strip tensile test. A fabric of areal density 350 gram per square meter is tested for strip tensile strength with 5 centimeter wide strip and 20 centimeter gauge length. So 5 centimeter wide strip and this is the 5 centimeter wide and 20 centimeter length. So 25 centimeter. Gauge length. If the breaking load is 550 Newton, the tenacity we have to calculate. Tenacity we have to calculate in centinewton per tex. So breaking load is given 550 Newton. So breaking load 550 Newton. That means 5,000 centinewton. Okay, this much centinewton is there. Now length of the material is 25 centimeter. And what is the mass we have to calculate? So if the mass is W, so by knowing if we know the mass per unit area, so we know the area of this section, we can calculate the total mass m gram. And for m gram, the length is 25 centimeter. So 25 centimeter length weighs m gram. So what will be the weight mass for 1 kilometer? That will be the text of this fabric section. Text we can calculate. So you can see the actual area is 125 centimeter squared, means 0.0125 square meter, and 3550 gram per square meter. So the mass of the test specimen is 4.375. That is the mass of test specimen. And the length of the strip is 0.25 meter. So we can calculate the text of the strip. So linear density in text of the strip is for 1000 meter 1 kilometer, it will be 17,500 text. And the breaking load of the strip is 55,000 centimeter. So we just divide by the text value, we will get 3.14 centinewton per text. This centinewton per text is the tenacity of the fabric. It's not the tenacity of yarn. Now, if we know the yarn tenacity, individual yarn tenacity, and if we know the number of yarns in a strip, so we can calculate the total load carried by the yarn. Okay? And whether this total load carried by the yarn will be equal to the fabric load, the total load carried by the fabric, that we have to see. Okay? Now, which is actually expressed by the fabric assistance. Fabric assistance factor is basically given by the relationship. This is the fabric assistance factor. The fabric assistance factor in any direction is calculated using the following relationship. It is fabric strip strength divided by single yarn strength and number of threads. So here that we will discuss, fabric assistance percent is typically more than 1. Suppose we have in a strip testing, when we test the strip, suppose there is no cross end, say what position? Here in each thread, suppose the strength is S for each thread, and in this strip there are n number of threads are there. N number of threads are there. So the strength, total strength will be S multiplied by N. Total strength of the threads is multiplied by N. But if it is 1, then cross ends like web threads are, when we impart the total breaking load will be S fabric. This S fabric will be more than total strength by work thread, ST. So that the ratio of S fabric by total strength is called S fabric. This is called the fabric assistance. Fabric assistance is always more than 1 because in addition to the thread under tension, the friction between the cross threads will also assist towards the increasing the strength. So that's why it's called fabric assistance percent. We can express in terms of percent also. Now let us see the numerical. The warp and web strip tensile strength with effective 50 mm width strip are 625 and 500 Newton respectively. Work strip strength is 625 and weight is 500. The fabric is made of 10 tex warp and 15 tex weft yarn with thread densities of 60 inch per centimeter and 40 picks per centimeter. The tenacities of warp and weft yarn are 20 cm per tex and 15 cm. Okay, respectively. Calculate the fabric assistance factors for both warp and weft. So width of strip is 50 millimeter. Or 5 centimeter. In warp direction, the linear density of warp 10 tex, tenacity of warp yarn, individual warp yarn is 20 centinewton per tex. So breaking strength of single warp yarn is 200 centinewton or 2 Newton. One warp thread will be 2 Newton. And thread density is 60 ends per centimeter. So total number of thread we can calculate. Total number of warp yarns in 5 centimeter will be 300. And strip strength is 625. 625 is the strip strength, and fabric assistance factor in warp direction we calculate by the relationship where fabric strip strength is given 625 and total number of threads under load is 300 and the single yarn strength of warp yarn is 2 Newton. So we can calculate the fabric assistance as in warp direction 1.04 and in wave direction similarly we can calculate the fabric assistance. So breaking a strength of single wave yarn is 2.25 Newton. The number of threads can be calculated. We know the thread density is 40 picks per centimeter. Total number of threads are 200. Using the relationship, when the strip tensile strength in wave direction is 500 Newton, same relationship we can calculate the fabric assistance in wave direction is 1.11. So fabric assistance in wave direction is more than the wave warp yarn which warp direction which we have got from the given data.
Our next numerical is it's a fabric tenacity measurement. Okay. So the numerical is the fabric of aerial density 350 gram per square meter is tested in a tensile tester for a strip tensile test with 5 centimeter wide strip and 20 centimeter gauge. The breaking load is found to be 400 Newton and tenacity we have to measure. Okay. It is in centinewton per tex. So, we can see here a fabric, a rectangular fabric where the dimension is given, its length is 20 centimeter and the width is given 5 centimeter. Okay. So, the breaking load is given 400 Newton, 400 Newton. So, first we have to calculate the Tex of the material. Okay. So, because we have to calculate in centinewton per Tex. So, it is a linear density. So, we have to first calculate the area of the test specimen. So, 20 centimeter is length and 5 centimeter is width. So, total area is 100 square centimeter and the is a 0.01 square meter. Okay. So, we know the area and areal density is given 350 gram per square meter, and if we want to get the actual mass. So, actual mass we can calculate, it is a 350 multiplied by 0.01, it is a 3.5 gram. So, this 3.5 gram weighs, its actual length of the fabric is 20 centimeter. 20 centimeter length of the fabric weighs 3.5 gram. So, from there we can calculate the Tex of the material. So, Tex is length of the strip is given to 20 centimeter is 0.2 meter. So, and Tex is basically mass in gram per 1000 meter. So, 1 kilometer. So, 0.2 meter material weighs 3.5 gram. So, from there we can calculate for 1 kilometer or 1000 meter what is the mass. So, in gram. So, 17,500 gram or 17,500 Tex. So, 0.2 meter weighs 3.5 gram. So, 1000 meter weighs. So, we can calculate that is actually 17,500 gram. So, that is the Tex. So, from there we can calculate the tenacity. We know the breaking load is 400 Newton. So, our unit required is centinewton. So, 400 multiplied by 100 to make it centinewton. So, it will be say 40,000. So, 40,000 centinewton divided by Tex. So, it is a 17,500. So, we will get centinewton per Tex. So, we can calculate the tenacity. So, 40,000 divided by 17,500. So, that will be actually the tenacity of the fabric will be 2.28 centinewton per Tex. So, in this way we can calculate the tenacity. Let us take another example, the similar numerical where the dimension is given 25 centimeter length and we will get the width is given 4 centimeter. Okay. So, 25 centimeter multiplied by strip dimension is length is 25 centimeter and width is 4 centimeter, and the mass per unit area is given 120 gram per square meter and the breaking load is given 20 kg. So, we have to calculate the tenacity in terms of gram per Tex. So, we can do this numerical in the similar fashion. So, first we have to calculate the area under the area of the sample. So, here width is given, so 4 centimeter and length is given 25 centimeter. So, total area will be 4 multiplied by 25, so 100 square centimeter. So, from there we can calculate the actual area of test specimen, it is 0.01 square meter, and then the area is given. From there we can calculate the mass of the actual mass of the material. So, 120 gram per square meter. So, the total mass of the specimen will be 1.2 gram. So, from there we can calculate the text of the specimen with the gauge length 25 centimeter. So, from there we can calculate the text of the strip, it is a 4800 text. So, that text will be used, and for to calculate the tenacity, breaking load is given. So, 20 kg, that is, so if we convert it in terms of gram, so to 20,000 gram divided by 4800. So, we get the value of the tenacity, we will say 4.16 gram per text. It is basically gram force per text. So, in this way we can solve different problems. Let us take a next problem. Here 700 Newton is the breaking strength, and the strip dimension is 250 millimeter, and width is the it is a 50 millimeter. So, from there we can calculate the mass of the material. So, the mass per unit area is given 300 gram per square meter. From there we can calculate the actual mass. So, actual area is 0.0125 square meter, and from there, and if we multiply by 300, so it will be 3.75 gram. See, 3.75 gram is the actual mass of the fabric strip, and length of the strip is 250 millimeter. So, that is 0.25 meter. From there we know the mass and we know the length. From there we can calculate the text of the strip, like we have done in earlier case, it is 15,000 text. So, we know the text of the material, and we know the breaking load, it is given 700 Newton. So, we need to calculate in centinewton per text. So, 700 Newton means 70,000 centinewton, and divided by 15,000 we get the tenacity 4.66 centinewton per text. So, in this way we can calculate the tenacity of fabric. So, till now we have calculated the strip tensile strength, but for our daily application the another type of testing is required. So, graph test. So, strip form we test, and the all are in actual it is not been used. So, it is not gripped in actual fashion. So, what we know, we need to test the material which is gripped at a particular point. We do not grip in the basically the whole width. So, we can measure the other type of test, like in that this is the type of test which is required in regular basis in the actual practical application. Let us first do another numerical of a polyester filament tenacity. So, here 200 denier polyester filament with a breaking strength given 8 Newton. Now, we have to calculate the tenacity of the filament in centinewton per text. So, here it is 8 Newton is given, we have to calculate first centinewton. So, it is becoming 800 centinewton, this is the breaking load, and we have to calculate the linear density 200 denier. If we divide 200 by 9, it will become the text. So, from there we can calculate the tenacity. So, it is a 22.22 is the text, and 800 is the centinewton. So, 800 is the breaking load. So, if we divide 800 by 22.22, so then we will get the tenacity in centinewton per text. So, therefore, the tenacity is 800 divided by 22.22, it is at 36 centinewton per text. Okay. So, we will be doing a new type of test basically what we have tested. So, the strip textile test, strip fabric testing in the strip form, but here the another type of test it is a which is the wide width fabric. So, in most of the applications we do not actually face this type of problem where the fabric is actually gripped in entire width, but in most of the applications we use the this type of loading pattern where fabric is gripped at the center of the material, it is not in the whole width. This is known as grab test. So, grab tensile stress is fundamentally different from the strip test. Okay. So, jaws are considerably narrower than the fabric and fabric width, entire width. So, if we see this is the fabric width, and if we see the jaw is considerably lower width than the entire actual fabric width. Okay. So, in this way we can actually measure the strength. So, no need to fray the yarn. So, in what we have seen in case of strip test, so we take out the edge yarns, these edge yarns we take out just to ensure. So, fraying is there. So, this fraying is required just to ensure all the yarns are gripped by both the jaws, top jaw and bottom jaw, so that proper strength value is actually obtained. But in grab test we do not need this type of fraying action. So, to test quicker and simpler way, so we simply cut the sample and the grip is done at the center. So, here speed is adjusted so that the sample breaks at 20 plus minus 3 second. So, this is as per the BS standard, British standard. We get this time, we have to adjust the speed in such a fashion that it breaks at 20 plus minus 3 second. So, effectively grab strength is it is generally higher than the strip test. So, here certain amount of assistance from the adjacent yarn to the central stressed area is we get. So, which we do not get in case of in case of strip test. So, this due to this adjacent yarn, so we get the higher strength than the revealed strength. Okay. So, we have actually completed the tensile characteristics of the material. So, next we will discuss with different types of mechanical characteristics in our next session. Okay. Till then, thank you.